So in the first part, we talked about kind of mineral resource processes in general, and then we focused in on some of the igneous processes. They're listed here. What we're going to do now is do the metamorphic, sedimentary, biological, and talk about some of those different processes. So in the previous slide, we did mention contact metamorphism. That is what happens when molten rock comes into contact with existing rock. We can also have regional metamorphism. That's when a whole area, due to burial or tectonic conditions, becomes altered by heat and or pressure. And so metamorphic activity on a regional basis can produce a large area of a certain type of rock, or it can be still kind of concentrated. And those rocks, a lot of times this produces a whole rock resource like marble or slate, rather than some specific type of mineral. However, we can get areas due to hydrothermal metamorphism, so hot water bringing new material in can alter, for example, limestone into talc, which is what's used in baby powder. Regional metamorphism can produce anthracite coal. It can also produce graphite. So there's a lot of different types of metamorphic rocks that can be produced by this process that are then valued for their characteristics. Moving on to sedimentary processes, there's just a kind of a list here. Sand and gravel deposits are very important. If you want to look at Lab 17, number 4, there's a whole lab on sand and gravel deposits. Ore and mineral deposits, one of the really important ones in this category are what we call placer deposits. So because sedimentary processes like moving water will pick up and drop off materials based on their size, their shape, their density, their overall weight, you will find certain minerals placed in certain deposits because of their mass, density, size, etc. So those are called placer deposits. And probably one of the best examples that people are familiar with would be gold. Because gold is very dense, it tends to settle out with larger sediments because it's settling out by weight rather than size, and the density makes it very heavy and hard to move. And so in a place like a coarse sand or gravel bar, that's the kind of place where you'd expect to find little bits of gold. And that's where people will pan for gold. So this is an example of some of the different places where you might look for a placer deposit. You can see in what's called a riffle where there tends to be larger rock particles, but kind of spaces in between there where the water slows down. That's where the heavy particles that are the size of little gold fragments or even sometimes a nugget will settle out. They'll tend to settle out with the gravel. You can also see places in a pool where they might settle out in fractures in the rock. So that is what a placer deposit is. You can think of it as the river is placing the material in a certain spot based on its physical characteristics. Evaporite deposits are another important type of sedimentary process, and this is what you get when water evaporates. Now this shows a natural environment where water is evaporating and leaving some kind of mineral crystal behind. That's the white crust. It could be sodium chloride, it could be calcium carbonate, it could be gypsum, it could be several different things. So it just depends on the chemistry of the water that's evaporating. This is also an example of a natural process that humans can mimic. So if you're near the Great Salt Lake, you can isolate a section of the lake, allow water to flow in, close it off, the water evaporates, you let some more water in, close it off, it evaporates, and over time, you will create a deposit of whatever minerals are crystallizing out of that water. We actually do something similar with the placer deposits. We can create kind of a system that mimics what nature does. But nature, because it can do this for an extended period of time compared to human time scales, can produce huge deposits of things like evaporites. And this shows you where some different old evaporite deposits are found. You'll notice these deposits around the Gulf of Mexico. Those, geologically speaking, are relatively young. There are much older deposits up in Michigan. These are several 100 million years old, for example. Calcium carbonate is an important deposit, as are brines. And a brine means that you can drill down into a rock layer and pump out a mixture of water and whatever that evaporite deposit would be. So you can either do this naturally, like you can drill down into these deposits and the water that's naturally going through there will have high concentrations in it, or you can pump water down and when it comes back out, it's got a lot of the mineral dissolved in it. Another example of a sedimentary process that is chemical is the process that produced what we call now the banded iron deposits. And these are chemical precipitates that settle out of the early ocean. So early in the Earth's history, there wasn't any free oxygen at the surface or in the ocean. Bad for life, or for a lot of life. And when life shows up and starts photosynthesizing and adding free oxygen to the environment, the iron that was dissolved in the oceans at the time reacted with that free oxygen, formed iron oxide, and settled out and gave us what we call the banded iron deposits or banded iron formations. This is a process that could be active today, but there's just never enough iron concentrated in the ocean to allow for an iron deposit, because the iron that shows up immediately finds some oxygen and settles out, and it becomes trace amounts in many sediments, but not amounts that would be mineable. So moving on to biological processes, these are things where living organisms take material out of their environment and then produce potentially deposits. And the most common example of this is one of the most common rocks at the Earth's surface, which is limestone. And limestone is typically made up of the shells of organisms that use calcium, carbon, and oxygen. So calcium carbonate is the most common shell material. And when those organisms die, whether they're large enough for you to see or microscopic, those shells make deposits that then turn into limestone. Animal excrement is typically rich in phosphorus, and so we get phosphate deposits from bird guano and bat guano. We can also get phosphate deposits from bones. Your bones are made of calcium phosphate instead of calcium carbonate. So if you get a lot of those bones in a collection in an area, then you can get some phosphate deposits. Weathering is another process that can produce concentrations of minerals. This shows something called residual minerals from a rock body. So the parent igneous rock is on the right. And in this case, that igneous rock has concentrations of aluminum that wouldn't be mineable and wouldn't be in a form that would be easy to get out of the rock. But when that rock is exposed to weathering processes, so basically it's exposed at the Earth's surface, rain falls on it, there are probably vegetation on top, and the rain combines with the dead vegetation to make a weak acid, carbonic acid, and that can help tear apart the rock. And essentially what happens is a weathering front, a geologist would call it, moves through the rock. So the first thing that happens is some of the minerals in the rock turn into clay. And if you continue that process, if you keep dumping rock on it, a lot of the minerals that are present in the rock will dissolve and go away. One of the minerals that does not dissolve very easily, or one of the elements that doesn't dissolve easily, is aluminum. And so it is left behind. So over time, as more and more elements are removed, the concentration of aluminum goes up because it's sticking around. And eventually you get a deposit that we refer to as bauxite, which is aluminum oxide. And so that's one of our most important aluminum ores. You can see residual ore deposits and secondary enrichments. Again, the weathering process is happening here. In this case, there is an ore body that one might already be interested in mining anyway, and then the weathering process can concentrate certain elements as it removes others and takes them away. We also know that there are elements in the sea, on the seabed. A lot of these are associated with mid-ocean ridges or igneous systems. So you can see the water soaking into the rock here. Dissolves materials as it heats up. Hot water does a really good job at dissolving materials. And then when it comes back out at the surface, it hits ocean water, which is quite cold. And that quick change in temperature results in the precipitation of minerals. And so that's what we have going on here. So that's deep ocean floor stuff that we might find at ocean ridges. We can also find a specific kind of marine deposit called a manganese nodule. I might have one of these in lab for you to look at, but it's a mineral precipitate that it forms on the seafloor. So that's more of a sedimentary process. And you can see the high concentration of metals that we often find in manganese nodules. Plate tectonics, which we mentioned early in the semester, impacts many of these rock-forming environments, especially igneous and metamorphic environments, to some extent sedimentary environments, because it can move those deposits around as the plates move, and it can also expose rocks. So when two plates crash into each other and maybe a mountain range forms, that's going to push rocks that form deep below the surface up to the point where erosion can expose them. So plate tectonics is important to understand if you want to have a general idea of where certain types of rock forming environments are going to occur or may have occurred in the past. And then last but not least, I'm going to mention just briefly extraction, how we get these out of the ground. In a couple of weeks, we'll have a deeper discussion on the impact of mining. But these are just some pictures from the mining that occurred in southwest Wisconsin, northwest Illinois, when they were looking for zinc. They would dig some shaft mines, and you could see how they would lower people down in there till they found the ore deposit, which they would then dig out. They could upscale their operation. You can see now they've got a motor on there. They can haul more stuff out. You can see the miner now has a bigger bucket, and the engine can pull that out. And then if you get into a really large scale operation, it can look something like this, where you're actually driving trucks into the ground and using that, trucks and conveyor belts, to take the material out. And then we can also do surface mining, where we just dig a big hole in the ground. If the material is close enough to the surface, we just start at the surface and work our way down, finding the material that we want, putting the slag material off to the side. That's just the extra stuff that we're either not interested in or the byproduct of processing the ore material. And that's it for this. And you can find more information, as I said, in the textbook.